2, 3. We're Corey Boone, Caitlin Williams, and Errol Munoz, and this is Lab 9 Michelson Interferometer Applications. We're Lab Section G.
Using a Michelson interferometer setup, we can adjust or measure the properties of two-point interference by simply adjusting one of the mirrors to measure the wavelength.
The micrometer used to shift this mirror needs to be calibrated to our experimental setup. We used this formula to calculate the calibration factor, and we needed to shift the micrometer 100 fringes past. Then we used a wavelength for the Heaney laser used, and this delta S is the shift found on the micrometer. With this, we multiplied it by 2 because we're using a mirror, and we found a calibration factor of 0.92871 microns.
3.
To find the wavelength of the mercury source, we shifted the fringes to past 50, and then the shift was 14 on the micrometer, giving a wavelength of 520.1 nanometers with our calibration factor. And the given value was 546 nanometers, so we found 2.2% error. For the sodium source, we used the same 50 fringe procedure and got a wavelength of 575.8 nanometers and a percent error of 2.2.
We derived this equation for the fringe intensity.
3. For spectral line separation of the sodium source, we started with circular fringes and the micrometer set to 0. We then adjusted the micrometer and recorded every time that the fringes disappeared. These are the separations of those fringes, and we took their average to plug into this equation, get the separation of the wavelength, which was actually a 5.43% error of the given value.
To measure the refractive index of air, this pump was placed between the beam splitter and the mirror so that the pressure inside the chamber could be changed to view its effects on the refractive index of air.
3. The circular fringes expanded out as the air was pumped out of the chamber, and they collapsed as air was let into the vacuum chamber. We observed a change of 20 fringes with a change of pressure of 46 centimeters of mercury. The length of the vacuum chamber was 44.65 millimeters, and the temperature of the room was 22.5 degrees Celsius. This equation was used to find the change in refractive index over the change of pressure, and the refractive index at 1 atmosphere was found to be 1.000316. These values were used to find a linear equation for refractive index as a function of pressure. This is a plot of our equation for refractive index as a function of pressure.
Go.
Alright. The change in refractive index at 2 points of pressure was 1.4177 times 10 to the minus 4 centimeters of mercury. Using the pressure data in Tucson and the temperature of the room, the refractive index of the room was found to be 1.00572364 air. This equation was used to find the refractive index of air at T equals 0, which was 1.00059, which showed that refractive index decreases as temperature increases. This other equation was also used to find the same refractive index of 0.1003327, which had percent error of 0.02571 from the other value.
3.
These are the heights given above sea level and for campus and Mount Lemon.
3.
With the values given in the lab report, we made a linear regression to find a formula for the pressure at Mount Lemon and the pressure on campus.
3.
This gives a pressure difference of 13.9 centimeter mercury, and with the values calculated in Part C of the lab, we got a fringe separation of 6 fringes. This indeed indicates that we are using a good enough window